Hello, Radical Algebra 1 students, and welcome back to your third lesson in Topic 6 about exponents and exponential functions. Today is going to start off a little bit weird because we're actually not going to do much with exponents on the first couple pages of your notes, but then it'll all fall into place and you'll realize it's been exponents the whole way down. So, we're going to begin today by looking at the title of our lesson, which is Radicals, Roots, and exponents. And you might have learned in middle school, depending on if it was COVID times or not, what a square root or maybe even what a cube root was. If you didn't, though, that's okay. We're going to learn that over the next, 45 minutes or so. But let's see what you guys can figure out first. There are 6 vocabulary phrases on your paper. Those phrases are square root, cube root, radical, radicand, perfect square, and perfect cube. Your job is to use your phone and your brain, and maybe your neighbor's phone if yours is dead, to decide what each of these phrases means. You're looking for a definition that you can understand. So if the square root definition says something like the radical of the radicand that returns a number when multiplied times itself gives the radicand, that doesn't make a lot of sense. You need to put the definition in your own words. And what some students have found easier in the past is they've started with an example and then they've used that example and said, oh, I think I get it now, to write their own definition. So let's take about 10 minutes or so and work through these 6 definitions, important phrases for today. Then once you're done, your teacher will unpause this, or you will unpause this, and see how you did. Ready, set, go. All right, well, let's look at these examples first. A nice square root example might be something like the square root of 9. I'll zoom in on that, sorry. Now, some students think that a square root takes half of a number. But remember, half of 9 is 4.5. The square root of 9 is not 4.5. The square root of 9 is equal to 3. How come? Well, that's because if you do 2 3's multiplied together, right, that's 3 squared, then the answer is 9. So how do we define a square root? That's a little bit tricky, and I'm actually not going to give you my definition. I'd rather you come up with your own, because it's important to you, right? You could say a square root is when you find the answer to a number when it's another number and it's multiplied by itself to equal the original number inside the square root. Whatever sounds good to you. But we do need to understand how a square root is used, and you apply a square root to a number to find an answer. And that's the answer because when you do 2 of that number multiplied together, it equals the number back inside. If you wanted another example, and I didn't accidentally turn on the settings in the middle of this video, there we go. You could look at the square root of 25, and that is 5. You'll also notice on my square roots I put this little tail at the end. One of my professors did that in college, and I copied him, and I've just done it ever since. You don't have to do that, right? This is also very similar to the division sign, which you learned a long time ago, right? Maybe 3rd grade or so, but it's not the division sign. It means something else. This is the square root of 9. Well, if that's the square root, let's look at a definition, or at least an example of the cube root. The cube root is written like this, and maybe I'll do the cube root of 27. The cube root of 27 also equals 3. And it equals 3 because, and I'm just abbreviating because with BEC so I don't run out of room here, right? Because 3 times 3 times 3, how do we write 3 3's? Oh, that's 3 to the 3rd power is 27. So it's very similar to a square root, but a square root is looking for 2 of the same number. A cube root looks for 3 of the same number. And now you might be thinking, well, wait, are there other roots? Could you have, how would you say, a root with a 4 right here? Well, certainly, you could do something, we call this the 4th root. We get much less creative after the cube root. The 4th root of 16, for example, is 2. And that's because 2 times 2 times 2 times 2, or 2 to the 4th, is equal to 16. You could have a fifth root, a millionth root, whatever root you want. However, the only two we're really going to focus on today are square roots and cube roots. So a little bit more vocabulary. What is a radical? Well, that's actually this fun little check mark symbol. So if we talk about the radical symbol, sometimes you'll hear it called a radical, sometimes you'll hear it called a root. They really mean the same thing, and they're just this cool check mark symbol. The radicand is the number that's inside the radical. So 9 is the radicand. Now on to our last ones, perfect square and perfect cube. Well, let's go ahead and work with that perfect square idea. A perfect square is when you pick a radicand, when you pick a number inside the radical so that you get a nice, think of that in quotes, answer. So for example, the square root of 16 is 4, which means that 16 is a perfect square. However, does anybody know what the square root of 17 is off the top of their head? No calculators now. Well, I don't know. It's going to be some decimal. It's going to be a number a little bit bigger than 4. It's going to be 4 point something, but I don't know what. Because it's not a nice number, because it's a decimal, we say that 17 is not a perfect square. And perfect cubes are the same idea. So what's an example of a perfect cube? Well, let's do the cube root of 125. That is 5, by the way. And so we would say that 125 is a perfect cube, and that's because we got a nice answer, right? So this cube root of 125 is 5. However, if you tried the cube root of 126, it would be 5 point something, but it's not a nice number, it's not an integer. And so 126 is not a perfect cube. In fact, during this unit, and actually for the rest of this semester, it's going to be really useful to have a reference of perfect squares and perfect cubes. So let's take a quick second to list all of the perfect squares from 1 to 256. Woof! Does that mean every number from 1 to 256 is a perfect square? Well, no. 1 is a perfect square because when you do the square root of 1, you get an answer of 1. The next perfect square after that is not the square root of 2. I don't know what the square root of 2 is. By the way, some students think it's 1. It's not. What's 1 times 1? 1 times 1 is 1. It needs to equal the radicand, the number inside. So we don't know the square root of 2. So that means that 2 is not a perfect square. I don't know the square root of 3, but I do know the square root of 4, right? The square root of 4 is 2. So our perfect squares then are the number that are going inside the radical symbol. 1 is a perfect square, 4 is a perfect square. I'll give you one more, and then let's see if you can figure out that pattern. The next one is going to be 9. And 9 is a perfect square because the square root of 9 is 3. Okay, now we're going to pause the video here, and you guys are going to try to find the perfect squares and the perfect cubes just using your calculator and maybe your group mates nearby. No cell phones for this, just your calculator. And I bet you guys will find some success here. And if you need a little hint, look at the answers that are going here. First 1, then 2, then 3. The next answer is going to be 4. And then the next one will be 5. And see if you can reverse engineer what the perfect squares are, because the numbers that I'm writing are not perfect squares. These are the answers when you do the square root of the perfect square. And I'll cheat and help you a bit. The very last one is easy because they told us we're going to 256, right? 256 is a perfect square, and it's a perfect square because the square root of 256 is a nice number. It ends up equaling 16. So we've got a few perfect squares here. You have 12 more to go, and then we have some perfect cubes. So go ahead and pause the video, take a few minutes, maybe 5 minutes or so, use your calculator to fill these in. Ready, set, go. All right, so hopefully you got your answers, and you can reverse engineer this by just taking the number that's here and squaring it. Right? If you do 4 times itself is 16. And so we know the square root of 16 is 4. 5 times itself is 25. 6 squared, 36. And you can do this on your calculator, right? We know where the square button is. You could do 7 to the second power on your calculator to get 49, 64, 81, 100, 121, 144, 169, 196, 225, and 256. By the way, aging myself here, you used to not be able to use calculators in our Algebra 1 classes, and you had to memorize this table. Luckily, we don't have to do that anymore. Let's look at those perfect cubes. If you didn't have time to do those, you can pause again, but I hope you did get a chance to get to them. So let's look at the first couple, and then we'll fill in the rest. 1 is our first perfect cube because the cube root of 1 is 1, right? 8 is a perfect cube because the cube root of 8 is 2. And we can see the pattern. The next one will be 3, then 4, 5, 6, 7, 8, 9, 10. Right? They even gave us a hint up here. The cube root of 512 is 8. So I know that over with this 8, the cube root of 512 is going to equal 8. So I guess I should have done it this way, huh? So this is 512 because the cube root of 512 equals 8. Let's fill in the rest. The cube root of 8 is 2. The cube root of 27 is 3. The cube root of 64 is 4. This one becomes 125. Okay, 6 times 6 is 36 times another 6. I think it's going to give us 216. Hopefully I'm not wrong here. We're just winging this. 7 cubed is 343. 8 cubed is 512. 9 cubed is 729. And 10 cubed is 1000. Being the math nerd that I am, I always look for these 5 cubes on a clock. And I'm like, oh, it's a perfect cube time. My wife loves that. She doesn't. Okay, so let's go ahead and move on to the actual lesson for today. We do need one more vocabulary term, sorry. One more vocabulary term that you need to be familiar with is the index, and I'll zoom in on that, the index of a radical. All radicals have an index. And remember, the radical, you see this up on your paper, is this kind of check mark. It's the root symbol. All radicals have an index. The index tells you how many of the same number you need to equal the radicand. For example, in a cube root, the index is 3. It tells you whatever number is in here, you need 3 of the same number to multiply to equal that. Right? If you had a 4th root, then the index would be 4. Of course, typical of math, there is an invisible number. There's an invisible index that we need to watch out for. Can anybody think of which type of radical has a hidden index, an index that we haven't had to write? I bet you've seen it before. It's even on this page, isn't it? We've done it all over the place. What index is hiding here? Okay, well, can you figure it out? If we look at the square root of 16, what do you think that index is that's invisible there that we didn't need to write? Well, the answer is 4 for the square root of 16, but why is it 4? Because how many 4s multiply to equal 16? Oh, yeah, 2 of them. So our index is 2. Yeah, this is one of the weirdest math invisible numbers. The square root has an invisible 2. Wouldn't it be nice if we could go back to the days where there were invisible 1s and invisible 0s? Whew. All right, so let's move on to the calculator. Everything we did on this first page, we didn't really need a calculator too much, except maybe the perfect squares, perfect cubes. But you will need a calculator for this part, and we'll explain why in just a second. So most of your calculators actually have 2 radical buttons. In fact, even your phones, and I'm really just thinking of an iPhone, but I think it works on an Android too. If you turn them sideways and you turn off rotation lock, you'll see 2 different symbols. You'll see a radical that looks like this, or sometimes it even has this guy right here. And then you're going to see a second one that has an X for the index. All right, so we're going to focus on calculators for just a bit, so make sure you're ready. Okay. Notice that a square root does have this invisible 2. We normally don't write an index for a square root. Okay? However, if we did, like we said, the index is 2 because the square root looks for 2 of the same number. So what we're going to do right now is compare the square root symbol and the x root symbol and see if they do the same thing. So on your calculators, let's go ahead and do the square root of 25. Now, how do you do that on your calculator? Well, I have my handy dandy TI-30X2S here. I still don't have an emulator for it, so if someone finds one, please let me know. To do a square root, notice that the square root is hiding down here above the x squared button. So to get access to that, our button combination is going to be the second button, which is right here. And then we're going to do the square root, which is actually accessed by pressing the x squared button. That's going to introduce a square root, and then we want to do the square root of 25. So we're going to go through, we're going to do second x squared, that gives us the square root, and then 25. And then I always like to finish by closing my parentheses, because when you do the square root, it opens a parenthesis right away, and then we're going to hit equals. We should know what the square root of 25 is. The square root of 25 is 5, isn't it? And so when you do that on your calculator, make sure you get 5. Show it to your neighbors. Show it to your teacher. Show it to your parents if you're doing this at home. You need to get 5. And again, we really should be using a non-calculator or a non-phone calculator because you don't get the phones on the test. Okay. So then what I'd like you to try and do is the same thing, that same combination of buttons, but now let's do it with the x root. So to do that, showing you your button combination this time, you're still going to press second. That's still your first move. But now you're not going to do the x squared key. You're going to go ahead and do this caret key that we've talked about before. That's the one you used to get an exponent. But that is going to bring the x root down. Then you're going to do 25, close your parentheses, and hit equals. Now, I don't have the same calculator here, but I've got a pretty similar button layout. This is a TI-84, and I'm just going to quickly show you, and I know it's hard to see on the screen. I apologize. And I'm going to turn off some math type here so that it looks a little bit similar. Oh, good, it's already off. A little bit similar to yours. So I'm going to do second and square root. Notice it gave you the extra parenthesis here, and then 25, and then I always close my square root at the end and hit enter. And that was 5, no surprise. Then I'm going to do the x root. My x root is in a different place than yours, and that's okay. But when you get the x root, it'll look like this. It'll probably say ANS in front of it. And then we're going to do 25. And there's no even parentheses here. You could probably close them. Let's see if that works. Oh, it didn't even work. It gave me an error, so I'll delete that. There we go. And we get 1.903. In fact, on your calculator, you might have even gotten a different answer, 1.903 with some other stuff going on. I'm pretty confident that 1.903 times itself is not 25. Well, does anyone have an idea of what the x root button does? If you're not sure yet, let's actually skip down to the next part and try something different with our x root button. So what we'd like you to do is to type a 2 first, then your x root, then 25. So if you're on the blue calculators, right, you're going to do the 2 first, right, this 2 key that's over here, then the x root, so second x root, 25, and then maybe no parentheses here, could be wrong on that, and then equals. Okay, and I'll show you what that looks like on my 84. So I'm going to do 2, and then I'm going to get my x root button. So you're going to have 2x root 25, hit enter, and we got 5. Coincidence? I think not. So this becomes 5. Did you get the correct answer? Yes. So take 30 seconds, pause this if you need. How does that x root button work? What does it do? Well, if you did everything correctly and you know how the x root button works, then go ahead and find the 5th root of negative 32 on your calculator. Do you see how to do it? Well, this 2x root of 25 What that ends up doing on your calculator is the number that's out front takes the position of x as the index. So it becomes the second root or the square root of 25. So if I wanted to type in the fifth root of negative 32, we'd do 5 and then the x root of negative 32 and then hit enter. And when you do that, I think you get negative 2. How come that's the right answer? Well, we should be looking for 5 of the same number, so let's see what happens if we do negative 2 5 times, like so. You can do that on your calculator if you'd like, or you can just do some mental math. Negative 2 times negative 2 is 4. This one is also 4. And then this one is still negative 2. 4 times 4 is 16. So now we have 16 times negative 2, and that is negative 32. So the right answer was negative 2 here. So the reason that our x root didn't give us the right answer before is because if you don't put anything in right at the beginning and you just try to do that x root, it's like, well, wait, what should I put in front? And the calculator tries to be too smart and says, oh, you guys must have wanted to take your previous answer up here and put it in for the index. I don't want 5 in, right? This previous answer is 5. I don't want 5 for my index. I don't want the fifth root of 25. I want the square root. So just be careful with that x root. It works, and you'll need it for cubes and fourth powers and all that fun stuff. But you need to be careful. Sometimes a square root, sometimes a cube root. Okay, there are 6 problems down here. These 6 problems can all be done on your calculator. In fact, you should try to use your calculator for all of them, even if you know the answer. Some of them are going to be perfect squares. Others are going to be decimals. If you get a decimal, please go out to at least 3 decimal places. Ready, set, go. All right, let's come back to this. Well, the first 2 are pretty easy. The square root of 0 is 0. Isn't 0 times 0, 0? And the square root of 1 is 1. Nothing too bad there. But I don't know what the square root of 2 is. So to my calculator, I'm going to do that second button and then the square root. And I'm going to do the square root of 2, hit enter, and we get 1.414. More digits after, but that's as far as we're going to go. And so what that tells us is if you do 1.414, right, and we'll even show you 1.414, and multiply it times itself, 1.414, we get an answer that's, so close to 2, 1.9993. Why isn't it exactly 2 if that's the square root? Well, it's because we didn't write enough decimal places. You have to go out further. Okay, so 1.414 is a reasonable approximation. Let's do the cube root of 3. That's the next one. To do the cube root, we need the x root. So I'm going to do 3. And then I'm going to bring my x root in. Remember, your x root is slightly different. So 3x root of 3. And we get 1.442. 1.442. Okay? And we could check that pretty quickly. We could do that 1.442 and then use the caret button on your calculator and take that to the third power, right? If you multiply this 3 times, it should equal 3. And if I do that, I get 2.998. Pretty darn close to 3. Okay, next one. The square root of 4 cubed. And notice 4 cubed is all inside the square root. So on my calculator, we'll do the square root. I'm in parentheses, so we'll do 4 to the power of 3, and then close my parentheses. We want to enclose 4 cubed in the square root. And we get 8. All right, that's pretty nice. Now let's do one more. This one wants us to do the square root of 4 in parentheses, and then the cube on the outside. So we need to be careful with those parentheses. Square root of 4, close your parentheses, cubed. Oh, still 8. Well, that's interesting. So a brief reminder, how do you type an exponent on your calculator? Well, that's your caret button. If you have a different calculator, it's a different button. But then if you follow order of operations, are the square root of 4 cubed and the square root of 4 cubed calculated the same way? Uh-oh. Okay, there we go. I don't know. Well, let's think about order of operations, PEMDAS. Which one of these letters in PEMDAS stands for square roots or roots? Well, I don't really know, actually. If you do the square root of 4 cubed versus the square root of 4 cubed, I think on this one we probably do the 4 cubed part, that's 64, and then the square root of 64 is 4. If we go this way, the square root of 4 is 2, and keep the cube, and 2 cubed, oh, sorry, the square root of 64 isn't 4, silly me, the square root of 64 is 8, and then 2 cubed is 8. It looks like we got the same answer, but we did a different order of operations each time. And usually when you can do a different order for your order of operations, it means you're actually doing the same operation. So I'm getting this weird suspicion that a square root and an exponent both fall under the E part of PEMDAS, and we can do them in either order. So does that mean a square root is actually an exponent? Or did we just get lazy and didn't want to write like R and E for radical, PEMDAS? Well, I don't know. Let's look at that. Connecting radicals to exponents. So don't forget, we're in the middle of a unit on exponents, so why are we talking about square roots? Well, let's remember an exponent rule from lesson 6.1. When you have the same base and you're multiplying, what do you do with the exponents? Oh, that's right, we add them together. So x to the a times x to the b is x to the a plus b. So let's go ahead and take an answer that I'm just pulling out of thin air. My answer is 9 to the first. Now, 9 to the first power just means 1 9. It's just 9, right? We were just writing in that invisible exponent. And so my question is going to be, if you had 9 to some power times 9 to the same power, and it equaled 9 to the first, what does the question mark have to be, remembering the rule up above? Do you know it? Do you see it? Really what they're asking is what plus itself equals 1? Well, if you phrase it that way, doesn't the question mark have to equal 1/2? Or 0.5 if you want, right? Because 1/2 plus another half is a whole. Right? Doesn't that suggest maybe that 9 to the 1/2 power times 9 to the 1/2 power equals 9 to the first power? But what is a 1/2 power? We've talked about positive powers. You just multiply the number times itself. We've talked about negative powers. It's 1 over a positive power. But what's a fractional power? Well, let's ask the same question as above again, but in a different way. Remember, 9 to a power times 9 to a power really means something times itself. These two numbers right here are the same, aren't they? 9 to the 1/2, 9 to the 1/2. So if I asked you the question, what times itself equals 9, then what does x have to be? Well, hopefully you said 3, because 3 times itself is 9, yeah? Well, I bet we can now probably give some meaning to 9 to the 1/2 power. We said 9 to the 1/2 times 9 to the 1/2 is 9 to the first. But also 3 times 3 is 9, or 9 to the first. So therefore, 9 to the 1/2 power is actually equal to the number 3. They do the same thing. They have to be the same number. Now just a friendly reminder, half of 9 is 4.5. So 9 to the 1/2 power didn't equal 4.5. So 1/2 does not mean 9 times 1/2. That's not the same as 9 to the 1/2. What operation do you need to do to 9 to make 3? It's not division or multiplication. Well, hopefully you said then that 9 to the 1/2 power, if that equals 3, means 9 to the 1/2 is actually the square root of 9. And you'd be right. A 1/2 power is actually a square root, just written as an exponent. In fact, the 1 and the 2 from the 1/2 are still there in the radical. Do you see where? In a square root, we know the index is always a hidden 2, right? So we know there's a 2 here. Where can you put the 1 so it doesn't change anything? Well, couldn't we put the 1 on the 9 right here? right? 9 to the first power is 9, and then there's a square root. So the 1 was attached to the radicand, and the 2 became the index. And so now we can actually see that all radicals, all roots, square roots, cube roots, anything like that, can be rewritten as an exponent. These exponents are often fractions. Sometimes they're known as rational exponents. Rational numbers are numbers able to be written as a fraction. And we can see it like this. When you have x to the ab power, the b is always the index. And I'll do this down here. This is the index. And the index goes right here. And I'll even put it over here too, because we're going to do it twice. The a is going to be your exponent. Now, these are both exponents. That's a little confusing. It's going to be the exponent that attaches to the radicand. And it can either go on the outside or the inside of the radical. It doesn't matter which one. And you'll see why sometimes it's better to do it one way versus another. So let's try this really quickly. Okay. Now, what we're going to do before we practice our weird fractional exponent thing is we're going to see how this actually works. Okay? So, if you had 8 to the 2/3 power, 2/3 can be split apart as 2 times 1/3. Isn't 2 times 1/3 equal to 2/3, right? 2 over 1. Yeah? And we know from previous lessons, lesson 6.1 again, that you can multiply these together. So 8 squared, I think isn't too bad, is it? 8 squared is 64, and we're still to the 1/3 power. Let's go ahead and practice our rational exponents from up above. Let's rewrite this using our root or our radical notation. The way we do that is we do a root over 64. And then we need to take the two numbers in the exponent and put them in the right positions. The 3 becomes the index, and the 1 becomes the power. The cube root of 64, I think we've actually seen that before. I'm going to jump back to my chart really quickly. The cube root of 64, oh, the cube root of 64 is 4. All right, so we can do that. And jumping back over here again, we have the cube root of 64. That's so exciting. This becomes 4, and then there's still a first power. And 4 to the first power is just 4. But what if you didn't think to do that? What if you split this in a different way? What if instead of leaving the 2 on the 8 and the 1/3 on the outside, you put the 1/3 on the inside and the 2 on the outside? Isn't 1/3 times 2 still 2/3? I think it is. Okay, so this becomes 8 to the 1/3 times 2, or to the second power. Let's do 8 to the 1/3 the same way we did the radical notation over there. We're going to do the root over 8. The 3 becomes the index, and the 1 becomes the power. Don't forget, though, we still have this squared sitting on the outside. Well, what is the cube root of 8? Use your chart. The cube root of 8 is 2. All right, 2 to the first power is still 2. And what's 2 squared? 2 squared is 4. So, if you are asked to find 8 to the 2/3 power, then it's not too bad. We're going to go ahead and bring the 3 down on the outside, and the 2, well, let's put it on the inside. Or do you want to put the 2 on the outside? It doesn't matter. Either one is okay. I actually really like to write the exponent that goes on the radicand on the outside because I like to make the number smaller first and then square it at the end. Some people, though, prefer to do the bigger number and then the cube root at the end. So I'm going to work with this guy right here, and so I'll show it the cube root of 8 squared. The cube root of 8 is 2. 2 squared is 4. So what this is really showing us then is that an exponent is the same thing as a radical and another power. And so that's why when we did this on the previous page, it actually got the same answer. You can do exponents in any order, and square roots are just a type of exponent. So this e right here, this exponent, makes way more sense in PEMDAS now that we know square roots and cube roots are actually just special exponents. So the last part of today are these 12 problems on the last page. The answer has been given to you for every single problem. Your job, though, is to prove to us why that is the right answer. And you can't, well, I mean, you can, but we are not looking for you to just type this into your calculator. It's actually a little tricky to type these exponents into your calculator. Instead, what we want you to do is show us the math, right? And I'll just give one example. I'll do problem 5 right here, just a random example. So on problem 5, let's see. The first thing I don't like on problem 5 is there's a negative exponent. But we know how to make negative exponents positive. We move everything to the denominator and make the exponent a positive. Then I'm going to rewrite this using my radical notation. The 3 is the index. I have to write smaller than I'm doing, but that's okay. And the 2 is a new power. We then need to find the cube root of 1,000, which is on your chart. That's 10. Don't forget the square is still there. And then 10 squared is 100. So I showed just through a couple quick steps how 1,000 to the negative 2/3 power is 1/100th. All right, so you have 11 more to do. Good luck. Please check with your teacher by the end. If you get stuck with anything, please ask. We're excited to see your success, and thank you for hanging out and learning how exponents and radicals are related to each other.